how Jay maintains his sanity. He goes and it's like meditation almost. It really is. I kind of need me and my horse time, or me and like something relaxing time. You just can't work all the time. Okay, so we had left off with Goldstein. And Goldstein was actually J.J. Johnson's boss. And what he did one day is he wandered in the lab while J.J. was doing his Crookes tube experiment. So you guys remember our picture of a Crookes tube. It's bad looking, but it's good. And bad looking, but it's good. We know that that had a negative, that had a positive, and we know that going in this direction, it gave off electrons, right? They traveled in straight lines. We know they have mass, they have shape, they have size. Johnson was doing all those experiments. Well, what Goldstein noticed is that coming off in the opposite direction in that tube was what we'll learn later is basically protons or the nucleus of an atom. And so when he characterized the positive piece of matter, because remember we decided that matter has two charges, right? There's positive and there's negative. We know opposites attract. So what happened is he noticed that that positive piece of matter, maybe I shouldn't use a dash because it looks like a negative sign, had some properties. First of all, it was positive charge, and it was different for each element. And remember, the thing that was interesting is that electrons were the same for each element. So now what we're discovering is that an element or an atom, that fundamental building block of matter that we said was indivisible when we were talking about Dalton, really can be broken apart into different pieces, right? And we're learning that one of the pieces is the same for every element, and that the other piece that it can break apart into is different for every element, right? And what he did is he realized, and we're going to learn this in like 10 minutes, so I'll spoil the idea, is that the nucleus of each atom contains different numbers of protons. That's why it's different for each element, but that a proton itself is the same for every element. Does that make sense? Okay, so, and I know I kind of go out of order a little bit, but we have JJ's plum pudding model now. So we're going back to JJ, and he came up with a plum pudding model for an atom. So what he said is that, well, what Dalton said is we have these indivisible things called atoms, and JJ said, okay, well, now we know we can break them apart, so there's got to be some structure, right? Some physical picture that we have of what these atoms look like. Now, do you guys know what plum pudding is? Yeah, it's a very British term because he was a very British scientist. I like to call it the chocolate chip cookie model. Plus, I like chocolate chip cookies. And what he really said is that the majority of the atom was made up of a large positive charge, and that in that positive charge was embedded these tiny electrons. Because remember, we know that electrons have a very small mass, and protons will have a very large mass, comparatively speaking. And so he said that the positive piece was that large cookie dough shape. Now, obviously, then different elements, so if we said that this is an example of, well, I put 8 electrons in it, so this is really oxygen, right? That a different element, say hydrogen, would have a different amount of positive charge, but the electron piece would be the same. And so this might be his concept of hydrogen. And so different amounts of positive charge, that's what Goldstein envisioned up here, right? It's different for each element, but the electron piece is the same between the elements. Does that make sense? And this is a wonderful model. And, you know, realistically, we're using this as an illustration of how if I do another experiment that this model can't explain, then I have to come up with a new model, right? And then if I do another experiment that that model can't explain, I have to come up with a new model. And so what you're going to see when we come back and cover this in Chapter 7, if I remember right, that we're going to pick up with the next model that we talk about, and we're just going to keep refining that model until we get to where our modern day model is, which is quantum mechanics. And so these are very rudimentary models, but they're good stopping points because they allow us to have some in-depth knowledge about these things. Okay, so the next person and the last, well, second to last scientist we'll talk about is Rutherford. And he did a huge number of different things, but he's most famous for two things. He did what's called the gold foil experiment. And by did, what I really mean is he told Geiger and Marsden, his lab assistants, to go do the experiment. So it's also called the Geiger-Marsden experiment. And what you'll notice is that a lot of these experiments and discoveries, the person that might be credited with it isn't necessarily the person that did the experiment if he was telling someone else to do it, right? Meaning it was his idea. And so Geiger and Marsden were his students. He said, go and do this experiment. And then they performed the experiment, and then he had the aha moment that said, wait a second, Thomson's model can't explain the results of this experiment. We have to have a new model. And so he made a breakthrough, right? Even though Marsden and Geiger did all the dirty work. And then you should recognize the name Geiger because Geiger counters. And Marsden, I'm sure he invented some famous things too, but not as obvious as Geiger, right? So it's not like, you know, Geiger was a slacker. He's got his own stuff. So the experiment that they performed was they took a radioactive source. And here's a whole other story that we could talk about. Because just about everyone has heard of Madame Curie, right? You guys all heard of her? She discovered radioactivity, won 2 Nobel Prizes, pretty amazing person. And so he's taking some things that he had gotten from her, which is this idea that you can have a radioactive source that emits particles. And they emit what is called an alpha particle. And what we know about an alpha particle is it has 4 mass units. And this is important for a reason. And then it has a +2 charge, meaning it's positive, right? What do we know about opposites? They attract. And so he took these alpha particles, and if you guys are really smart, I'll put it over here, but you don't have to write it down. We'll really realize that it's actually the nucleus of a helium atom, eventually, but not right now when they did the experiment. And he shot it at this really thin gold foil. So this is gold foil. And the reason they chose gold is gold is a very malleable metal, and you can pound it to be incredibly thin, almost to the point where it's only atom thick. And you can't do that with many other elements. There are a few, but they're even rarer and more expensive than gold. And so they use gold. Like you guys have seen gold foil like pendants, right? They can put like really thin coats of gold on top of the pendant. Or you can even have gold flakes and like, what is it, gold swaths? So, you know, you can even eat it if you want, or drink it in that case. And what he did is he made 3 observations. He first off realized that 99% of the alpha particles pass through unhindered. And by 99%, I really mean like 99.999 something percent. I don't remember the exact thing, but the idea is the vast majority of these alpha particles just went right through the gold foil. Now think about this. Gold is like, that's a solid that's supposed to not let things go through it, right? But, you know, if you shoot a small enough particle through it, it's got holes in it, is what we're going to discover. He recognized that in some cases they were deflected partially, deflected occasionally, and that very rarely they were almost deflected 180 degrees. And I put a quote in the handout, and I'll read it to you in case you don't have a handout sitting in front of you. But I love this quote just because of the language he uses and kind of the mental picture it makes. Because that mental picture isn't so great. Or I shouldn't say that mental picture, that picture I got before isn't so great. But he said, it's quite the most incredible event that has ever happened in my life. Now, you could argue maybe his life was boring, because maybe, but what he's really saying is that this simple experiment, this simple observation that most of them pass through, some of them are deflected, and then one other piece that we'll add in a second, was so groundbreaking that it just blew him away. It gave him such great insight into what an atom really was. And sometimes we look back and go, well, duh, I know what an atom is. Like if you had a good high school teacher, you know that there's electrons in the cloud, there's protons and neutrons in the nucleus, you know all this, right? But think about it, they didn't know this. And in fact, this is a direct contradiction we'll see of Thomson's model. So it's a big breakthrough. So it's the most incredible event that has ever happened in my life. It's as incredible as if I fired a 15-inch shell. Now, what does he mean by a 15-inch shell? See, this is old school stuff, right? Basically a cannonball. So he's saying if I took a cannonball that's like this big and shot it at a piece of tissue paper, it came back and hit you. So what are the chances that I take a cannonball, I shoot it at a piece of paper, it bounces off the paper and hits me in the face? I'd be pissed too if that happened. I mean, seriously, like if I took a cannonball and shot it through that wall, would you expect it to ever bounce back at you? And that's why he's saying this is the most incredible thing he's ever experienced, because it's basically shooting a cannonball at gold foil and then having that cannonball bounce back. And we'll explain what we mean by he considers it a cannonball in a second there. He said, on consideration, I realized that this scattering backwards must be the result of a single collision. And when he did some calculations, meaning he did some math that we'll do in a second, I saw that it's impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom is concentrated in a tiny nucleus and that it has a minute massive center that carries all the charges. So let's look what he means by that when he's talking about a model. So if we take Thomson's model, so remember this is JJ's model, and he's got this giant positive charge, and he's got these little electrons. And what he's saying is that if he took this positively charged helium nucleus, meaning it's got a +2 positive charge, this is light. This is on the order of 4 atomic mass units. Don't worry about what atomic mass units are or anything like that. It's not important at this moment. But it has a relative mass of 4. If we take a look at gold, now I'm going to forget, so I have to run over here. It's about 200 AMU. And so that's what he means by a cannonball. And then if we take a look at an electron, it's about 1/2000th of an AMU. And they knew this. They had these relative masses figured out. So what he's really saying is that if I take a semi-truck, and if I were to bounce it off of an electron, then that doesn't make any sense, right? Because an electron weighs 1/2000th. So this is saying if I take, to make it in relative terms, something that is 8,000 pounds, that's like a good-sized pickup truck or semi, right? Maybe a small semi. And I hit a gnat or a mosquito, who wins usually? The truck. But what he's saying is that if I took that truck and I hit that electron and I bounce back from it, then I ought to, that's not normal, right? If I drove my truck and suddenly I smash into a mosquito and my truck gets hurt instead of the mosquito, that's strange. That's why he said it's the most incredible event he's ever experienced. Because what he's saying is that what really should have happened is, first off, most of those atoms should have passed right through all of those electrons. And so most atoms, or I'm sorry, most in his model, sorry, not pass through, deflect. Sorry, got to remember who I'm talking about, right? In this model, most would be deflected because opposites attract and likes repel. So what he's really saying is that in Thomson's model, it's got that huge positive charge that's spread out, that those helium atoms should have been either deflected or absorbed and not passed through, right? And so what he's saying is I need a different model. In his model, what he's saying is take all of that positive charge and put it into a tiny little nucleus, then take those electrons and scatter them about in a giant cloud like this. Oops. And so then when you take your helium particle, that 4,2He plus 2, we should go down there, then notice that most of the time it's actually going to miss that nucleus because it's tiny, right? So this idea of tiny is because most alpha particles pass through, right? Bless you. Now, by most, remember we need 99.9999 whatever percent it is. I don't know if it's like 4 nines or 5 nines or something ridiculous like that. It probably says in the book somewhere or on the internet. It's just 99% is good enough for me. Is 99% good enough for you? Yeah, most of you would be happy with 99% in this class. Heck, most of you would be happy with 89.9% because that rounds up to an 8. So we can even go 10% less. So it's tiny because the alpha particles pass through. And then he knows that it has to be massive because the deflections that he sees are because you have something that's 4 AMU bouncing off something that's 200 AMU. And so that makes sense that 4 would bounce off of 200, right? Not the other way around. And, I mean, the electrons are still that, but when it encounters an electron, what happens is it simply gets deflected by a tiny little amount. And so we know that it has to be small. We know it has to be massive because of the deflection. So massive because of the deflections. And then the last thing he made is, is that we know it has to be positive because likes repel. So he kind of made those 3 observations, right? Tiny, massive, and positive. Because most things missed. When they didn't, they got bounced back pretty good. And we know that likes repel, right? That's 2 positive things would bounce off of each other. How do you able to do it? So what they use is like photographic plates around the edge. So if you look at the picture in the handout, you'll see that there's kind of this curved screen. And what would happen is when those alpha particles would hit the screen, they would do a mark or like a phosphorus or a glow. So that's how they could see it. See, this is old school. We can't do this anymore. We used to be able, like, you remember old school Polaroid cameras? If you took the undeveloped film and set it next to a radioactive source, you could see little pieces hitting it. And when you developed it, then you would see those little marks from it. Now, we don't have Polaroid film anymore, really, so we can't show that. So that's our Rutherford model. This is where in Chapter 7 we'll actually start from. And then we'll refine this model more and more. But this gives us enough information that we can understand the structure of an atom and we can understand basic chemistry based on using that. Now there's one piece of the puzzle that I haven't mentioned that we all know exists, which is protons, electrons, and neutrons. So we have James Chadwick. And this came many, many years later, 1932, if I remember right. He discovered the electron, or discovered the neutron. Discovered neutrons. And they're called neutrons because they have neutral, or essentially no charge. And they have a mass that's on the order of a proton. Therefore, he concluded that they belong in the nucleus with the protons. We'll also understand that they're necessary, because see, no one ever asked me this question. I think it's funny. Now, I said opposites attract, likes repel, right? So if I stuff all these protons in the nucleus, what really should happen? They should repel each other, right? But what we're going to find is that a combination of those neutrons and something called the strong nuclear force that we'll learn about next semester binds it all together, or allows it to not explode like that. But when you do manage to make it explode, we all know that like atomic bombs, nuclear bombs, and fusion bombs are all pretty huge, right, compared to the amount of mass that you explode. And so, you know, we'll learn about details like that later on. And realistically, the reason the neutrons were the last to be discovered is they're neutrally charged, so they don't interact with matter very well. Neutrons pass through your body all the time with no interaction occurring because, remember, opposites attract, likes repel. So in order for things to interact, they have to have positive and negative charges in general. And if they're neutral, they don't tend to cause much damage. Now, that being said, you dump enough neutrons through someone, you can cause damage, but we're not going to worry about that. Okay, so let's summarize some things that we know and then see how this affects chemistry. So we know we have protons, we know we have neutrons, and we know we have electrons. We know that we give them symbols because J's lazy. Protons are either a P or really I think they should call it P+, but most places don't. Neutrons are given the symbol N, and electrons are an E with a little negative sign. We know they have charges, and their relative charge is +1, 0, and -1. And this idea of relative means that we can measure the actual charge on an electron, and these are ridiculously tiny numbers, but we don't care what the actual number is. What we care is that it's equal and opposite to that of a proton, right? So relative charge, we'll realize that there's about 96,500 electrons per coulomb, which is what we normally measure charge in. Again, let's worry about that next semester. We can also talk about relative mass. And the relative mass is that a proton weighs about 1 AMU, a neutron weighs about 1 AMU, and an electron is 1/1832, if we want to be specific, of an AMU. Now, I usually just round that to 2,000 because that's close enough. Now, if you want to know the actual mass, I'm pretty sure it's got to be in your book. I don't know what page in my notes it is. I'm too lazy to go looking. Where is the... let's see. So a proton weighs about... Don't memorize this. I just want you to realize why we use relative mass units, because that's a pretty ridiculously small number to try to bother with. So much easier to say 1 AMU than to always say 1.6 times 10 to the minus 27 kilograms. And like that makes the mass of an electron 9.11 times 10 to the minus 31 kilograms. So we use relative units because they're way easier to keep track of and think about than the other sets of units. So we have relative masses, relative charges, symbols. We know their location in an atom is the nucleus, and in a large cloud. I forgot to mention this under Rutherford, but we'll mention it right here. So remember, the nucleus is small, massive, and positively charged. And so that cloud is very large, and that's where the electrons are with a negative charge. Now, to give you an idea of the scale of this, and this is what I forgot to mention under Rutherford, because, well, Jay's brain gets around a lot. Imagine a football in Mile High Stadium. Now, you guys have all been to a football stadium. It's pretty large. Frankly, you could even go down to the high school stadium. I mean, I know it's not the size of Mile High, but it still gives you an idea. That football is the nucleus. The size of Mile High Stadium is the electron cloud. And so one thing I want you to realize, if we go back in your notes and maybe make a little note, is like when I look at this picture and I drew a dotted line, what we're really saying is that if I kept the scale relative, there's a lot of space between those atoms, right? There's an entire football field's worth of space between each nucleus. And so you can see where it's very easy to imagine how everything would pass through that pretty darn easily, right? You could walk through Mile High Stadium and not hit that football a million times, right? And so it's weird to think about, because we were talking, and in this class we've talked about solids, liquids, and gases, and we said solids are like this, right? Well, no, solids are really like this compared to, say, the size of an electron or an alpha particle. But since we're pretty massive, you know, we perceive that as solid, even though really there are lots of holes. You could take and shoot alpha particles through this wall all day long. It's weird. Like I say, one of the tough things I think about chemistry is to visualize something that is that freaking tiny and then how it interacts with things. And it even gets worse when we realize it doesn't behave like what we think normal matter behaves like, follows the rules of quantum mechanics. And so that adds another level of difficulty. Now, that being said, all this information is wonderful, and I want you to know it, but the most important part is chemistry, meaning how does a chemist think about these things? Why is it important to chemists? Well, protons are important to chemists because the number of protons is unique for each element. And if you take a look at your periodic table, you'll see that hydrogen has the number 1 above it. That's how many protons it has. The next element over, helium, has 2 protons. You can go a bunch more elements and get to sodium, which has an 11 over it. That means it has 11 protons. So what's unique about each element is how many protons are contained in that nucleus. All elements have protons in the nucleus. How many they have changes their chemical behavior. And it's weird for me to think about it on that scale, that it's just like how many of each thing I put in there. You take an element that's a gas, to an element that's a solid, an element that's totally unreactive, to an element that's very reactive on either side, you know, things like that. So just the number of protons in the nucleus affects that. Kind of makes my head hurt. Okay, neutrons, I didn't leave a lot of room. We'll squeeze it in there. They're relatively unimportant. Unimportant because they do not affect chemical reactions. And so realistically, their only importance is the fact that they have isotopes and they're responsible for part of the mass of an atom. So every atom had a unique mass. That went back all the way to Dalton, right? That he said each atom had a unique mass. And what we're going to find is that that's not true, because atoms with the same number of protons can have different masses. They still behave the same in chemistry, so we don't care. Does that kind of make sense? And in fact, when we get to nuclear chemistry, we'll find out that the number of neutrons is important and does affect nuclear chemistry, but in regular chemistry that we do in beakers, no effect. So we tend to ignore neutrons. And so I hate to say they're not important, because then you guys will be like, oh, they're just not important. Well, I mean, they have importance, but for what we do, we ignore it. And then the last one is electrons. And electrons are either gained or lost to form ions. And remember, we had said cations are positive because we lose electrons, and ions are negative because we gain electrons, and they control chemistry. Chemistry is really about following around the electrons. Understanding what elements react with what other elements is all about the electrons and all about opposites attract, likes repel. So if you can keep track of the electrons, then you understand chemistry, which is why we'll come back in Chapter 7 and learn a lot more about electrons. We'll come back in Chapter 8 or 9 or whatever chapter it is and learn about Lewis dot structures. How many people remember that from high school? Yeah. And then, we'll even learn, I think the next topic in Chapter 2 is focusing on this concept of opposites attract. Okay, so let's take a look at this concept of atoms, cations, and anions. Keep this straight. You will hear the word cation and anion over and over and over and over. And you have to have a good fundamental concept of what these are, right, Parker? Just making sure you're paying attention. So atoms are neutral. And what that means is that the number of protons is equal to the number of electrons. Cations are positively charged because the number of protons is greater than the number of electrons. And what that implies is that I've lost electrons. And anions are negatively charged. The number of protons is less than the number of electrons, and that means that we had to have gained electrons. So remember, if we think about that Crookes tube experiment, we know that that metal plate can lose electrons, right? Well, it implies if somebody lost electrons, they had to be attracted to something that was positive, so somebody had to gain some electrons, right? So all of chemistry is whether you're a cation or an anion to start with. We'll understand that it's more difficult later, but we'll add the difficulty later, not now. And so if I think about a cation, what I'm really saying is that I take a neutral atom, so this is neutral, right? And that's not how you spell neutral, it kind of bugs me. And if I lose an electron, then I form an anion, or a cation. And this is that electron I lost. Did not mean to. Every time I accidentally tap the slide, that's the automatic thing that says go forward. I do that all the time, so I will always go back if I don't notice. But I also had to sneeze, and so I didn't notice. So now, what I want you to notice is that the way we write basic chemical reactions, now I should point out, go read in your book, they show pretty little pictures for this, but I am a lazy bum, and so go read the pictures in your book. I'm going to do this neutral because there's no cation being lost, right? This implies that I lost an electron, and that's the electron I lost. Now, one of the things I want you to recognize about chemistry is we know from conservation of mass, conservation of energy, that you can either create or destroy matter, right? That means we can't just create or destroy protons, and we can't create or destroy electrons. So notice, this element is the same on both sides, right? So I didn't create or destroy any protons, right? Here, this implies that I lost an electron, right? This is +1, that's -1. We're leaving the notebook for 1. Is 0, right? And notice the sum over here is 0. And we don't write that. And so to be less lazy as chemists, I'm going to only do it a couple times. We should put a 0 and a +1 and a -1 so we're not really lazy, right? Form cations by losing electrons. We write the chemical reaction implying that way. Now maybe I guess I'll be a nice guy and I'll just draw this. So if this is sodium, here's my sodium atom, right? What we're saying is that if I lose an electron, I get to make a sodium atom that only has 10 electrons plus that extra electron that's missing, and this one has 11 electrons. Does that kind of make sense? Yeah. I don't like the pictures because I'm lazy. The book has pictures, go read it. And if the book doesn't have pictures, my other chemistry book has pictures for sure. Now, if I want to show an anion, then, for instance, I'm going to take, say, chlorine. I'm going to add an electron to it. So notice, which side is the electron on now? The left side, right? And I make a chlorine anion. So I take a neutral atom. I add an electron, and I get a chlorine anion. Oops. And notice, if you do the math, both sides have a -1 on it, right? So I didn't create or destroy the electron. I showed the electron on this side, added it to the chlorine to make this, but I didn't destroy or create an electron, right? And then what I mean by electrons control chemistry is you should all know what sodium chloride is, right? That's the normal example everyone uses because I've yet to meet someone that doesn't know what table salt is. That opposites attract idea is that if sodium loses an electron, chlorine gains that electron, then they make the compound sodium chloride. So stupid. Opposites attract, right? So we're going to learn that our first rule is that if I know how many electrons something gains or loses, then I know that they can form a compound, and opposites attract. And so this is technically called an ionic bond, and we can know about that. And then remember, the other thing I told you is amazing is highly flammable metal, toxic gas, heat. I love salt. Salt enhances flavor. As a kid, I hated salt for some reason. Like, everything always felt like it was oversalted. As an adult, it's like, pour it on. Nothing better than salty, greasy French fries. Okay, let's talk a little bit about isotopes, though. And I might be going a little out of order just because I don't have a copy of your homework sitting in front of me, and I'm just kind of winging it. Someone have a copy of their homework sitting in front of them? I'll just make sure I don't forget something. Cal's way ahead. Oh, no. So 2A and 2B. Who's got them? Who's winning the race? Who's J admitting that you forgot to go look at the beforehand? There's 2B. Okay, 2B. So we drew those, Yep, we'll need to talk about it. Good, I'm right on track. So remember, what's the definition of an isotope? Has the same number of protons, a different number of neutrons. So they're the same element. This implies the same element. And what it's really saying is that Dalton's idea that elements all have the same mass is a lie, to a certain extent. They really can have different masses. So for instance, you can have a sodium atom that has a mass of 22 AMU, but you can also have a sodium atom that has a mass of 23 AMU. And what that implies is that I have 11 protons and 11 protons because sodium has 11 protons, right? How do I know that? I haven't memorized. You have to do what? No, I'm not that neat. Look on your periodic table. You get one on test, right? And so what this implies is that this also has 11 neutrons, right? Because neutrons and protons weigh 1 AMU each, approximately. And this implies that this one has, oops, not protons, 12 neutrons, right? So notice they have different mass, but they behave the same chemically. If you had a sample that was 100% pure sodium-22, then a sample that was 100% pure sodium-23, you would have no way to differentiate them in a chemical beaker, really. You might be able to get really creative and figure out how to do it, but I'm not sure that that's true. And so we can't distinguish between the two. The other thing to remember is that even a very small sample of sodium has almost 6.02 times 10 to the 23rd atoms. And so statistically speaking, any sample of sodium I take has a very specific ratio of this sodium and this sodium combined, and you know, to get an isotopically pure sample of either one of these would be a ridiculous amount of effort. That being said, scientists do go through that ridiculous amount of effort to get isotopically pure samples, meaning samples of just this or just that for very specific types of research. And in fact, one of the most obvious ones is when we get to the nuclear chemistry chapter, there's two types of uranium. One type of uranium is pretty much non-reactive in the nuclear sense. The other type of uranium is what makes nuclear bombs. Now, it turns out that 99.999 whatever percent of uranium is a non-bomb type, and so you just need a small fraction of that to do it. And so to make a bomb, you have to make an isotopic separation of the uranium. That's the hard part to making a nuclear bomb. Honestly, if you gave me an isotopically pure sample of uranium, pretty sure in my garage I could build a nuclear bomb. It's getting it apart that's the hard part. That's what's interesting, I think, about nuclear bombs. They're not hard to build. They're hard to make physically. Does that make sense? Not hard to build, but hard to make physically. It's hard to separate them. We'll talk about that when we get to the nuclear chemistry chapter. And so if we look on the periodic table, what is the number under sodium? See, I left one, right? So there's 22.99, right? So this is the average of all isotopes. And what it's really saying, if you kind of think about it, is that 99.9999% of sodium is sodium-23, and only about 0.00001% of sodium is sodium-22. Meaning most sodium has 12 neutrons, some sodium only has like 11. And I'm making the numbers up because the idea is that it's pretty extreme, right? And then there are other elements that have less extreme distributions. Let me look at my notes, because God knows I don't memorize isotope ratios in my brain. That would be like you guys memorizing how many protons each element has. Just a waste of your time when you have this lovely periodic table sitting in front of you, right? Or you should normally have that. So where is my example with numbers in it? Because if I have to make this up, it's going to piss me off, but I can do it. I'm just lazy, remember. And it looks like I may have to because I may have misplaced my example. Well, that's a bummer. That's okay. We make it up. Okay, realize that the math will not work out perfectly. Let us say that, let's see, we'll do chlorine. Say 55% of chlorine has 17 protons, and let's see, what is 17? What's 36 minus 17? That's like 19 neutrons. Yeah, it's 36, right? And that 45% of chlorine, and I already know I did this wrong because I did it backwards, but that's okay, has 17 protons. Oh, I forgot the P. Probably makes more sense than just 17, right? And we'll call it 18 neutrons. And so what this means is that this has a relative mass of 36 AMU, and this has a relative mass of 35 AMU. Now, please note, the real mass is probably something like 36.003279 and 35.12876, meaning a lot more sig figs than I'm in a real example than this one, okay? So I apologize for that, but you guys are good with numbers, right? If you have an example that has more numbers in it, does that make it harder? A little bit, because you got to use a calculator, but, you know, not harder. And so what it is that chlorine, or the average chlorine atom, is the weighted average of all isotopes. Now, I gave you 2 isotopes. Realize that some compounds have like 10 or 15 different isotopes available. But the nice thing is when you have 6.02 times 10 to the 23rd atoms, you always have a weighted average, pretty much exactly. Because that's just such a huge number of atoms. With statistical chances that you would not have exactly 55% and 45% is statistically pretty much 0. Probably win the lottery first, okay? And so the average then, chlorine, is simply 55% times that 36 AMU plus 45% times the 35 AMU. And realize when you do this example in the homework, it has more sig figs in it. Jay's lazy and lost his example. I apologize. That's like being a sloppy teacher. I'm setting a horrible example today. I come late to class. I lose my homework or my notes for lecture, because otherwise I don't make these up. So let's see, 0.55 times 36 is 19.8 AMU, and 0.45 times 35 is 15.75 AMU. And if I add those together, I get, 19.8 plus 15.75. Jay's not keeping track of mass very well, but the average chlorine sample should weigh 35.55 AMU. And so if you look on the periodic table, you see chlorine with 17 protons above it, right? And then it has a mass number below it. The real mass is 35.45. So obviously this is kind of a close guess, right? It really is not 55 and 45%. Jay made those numbers up, right? Maybe it's like 56 and 44% or something like that. So that's pretty good for guessing, right? In fact, this round's to 35.5. This round is 45. Crap. Anyway, it was a close guess. That's pretty good for doing it off the top of your head. That'd be an interesting experiment to make you guys do. Have to figure out the isotope distribution based on knowing the answer and making up the rest of the data. But we're not going to do that because we're not needed. Okay, so do you guys get this concept then? Where we're going to have different numbers of neutrons, going to give us different numbers of masses, but that we don't care because this number, we just read off the table, right? And this number tells us how many protons we have, right? And then all chlorine behaves the same chemically, meaning this chlorine and that chlorine is indistinguishable in a chemical reaction. That's what we said about neutrons, right? So what you'll find is that chemists ignore neutrons. Okay, one last topic, I think. Well, maybe, yeah, one last one. We'll maybe end early. So this idea of isotope notation. This is really an invention of physicists. So it's not 100% how chemists do it, but it's important to learn it. We'll use it in nuclear chemistry, and then I'll show you why chemists don't use the full notation, and we simplify it because we're lazy. So you always have an element, and we have three numbers. We have A, Z, and C. And each of those numbers represents something about that specific isotope of an element. The Z number is the easiest. It's simply the number of protons. It's sometimes called, and then A is simply the number of protons plus the number of neutrons. And the reason why they don't just put the number of neutrons up there is we don't care how many neutrons we have, right? We care about the mass. And so, the A is sometimes called the mass number. And then C is the charge. And we don't care how many electrons we have. We care about the difference between the number of electrons and protons. And so we have a subtraction there, right? And so here's the trick. You can always know from this notation how many protons, neutrons, and electrons you have. But we don't care how many protons, neutrons, and electrons we have, because what we care about is the number of protons, right? Because that tells us the element. We care about the difference, whether it's net positive or net negative, and then we care about the mass. And so the reason it's formulated this way instead of just protons, neutrons, and electrons is we don't care about the net number of neutrons and electrons. We care about some other piece of information. And so for an example, and there'll be a couple. If I have 11 protons, 15 neutrons, and 10 electrons. If I want to write that in isotope notation, then the first thing I do is say, okay, 11 protons is sodium, right? And the 11 goes down there, right? But I don't write 15. What do I write on the upper left? Right, 11 plus 15. So I write 26, because that's really protons plus not electrons, neutrons, or 11 plus 15. And I don't write 10 electrons over here. I really write plus 1 because I have lost 1 electron, or 11 minus plus 1, right? Does that make sense? And I know one thing I always forget is that if you haven't had chemistry class before, you might not know what a proton, neutron, and electron is, and you're lost like 2 topics together. But what I'm going to say is that I think you guys can all learn this if you just practice with it. That's why there's a couple homework questions on it. If you need more, I'll make up more. Sometimes I think I should put more on there. But I used to have lots and lots of problems on my homework, and I felt like that was just punishing people. And so then I put fewer questions on the homework, and I know there's a sweet spot for each individual that's different. Some of you need more practice, some need less. Does that one make sense? Now, what if I do the opposite? What if I say I've got that ion, and let's put 18.8. So now I'm saying how many protons, how many neutrons, and how many electrons do I have? So protons is easy. It's always the lower left, right? That's an 18. The number of neutrons is now not an addition, but a subtraction. 18 minus 8 is 10. And here's the tricky one. This one gets people mathematically. How many electrons do I have? So 2 ways to do this. Like I said, the electrons can screw people up. Do the math and simply put 8 minus x equals -2 and solve, and you get, oops, I'm sorry, wrong direction. You get 10, right? 10 electrons. Or think about this as that I have 2 extra electrons, and since I have 8 protons, 2 extras make 10 electrons, right? Because remember, number of protons and number of electrons is normally the same unless I have an ion. And then recognize that chemists are lazy. What a chemist really does is he says, who the fuck cares about half of that? Oops. Sodium. Oh, that's all I care about. Oops. So all the chemist cares about is that I lost an electron. I'm a cation. Notice, I don't write the number of protons because I have a periodic table if I'm a chemist, right? I don't write the mass number because I have a periodic table and I just go look that shit up too, right? Seriously. I mean, chemists are, yeah, go be a physicist, way more work. Oxygen minus 2 means I gained 2 electrons. I'm an anion. And if I need to know how many protons I have, I go look up on the periodic table. If I need to know the mass, I go look it up on the, because I'm a chemist and lazy. And then recognize that if I were to make a molecule out of this, what would I do? Advanced 101 question here. What compound would this make? Meaning this is, man, today's already Wednesday, we have tests on Friday. This is actually Monday's lecture. Think about it this way. If this loses an electron and this has to gain 2 electrons, then how many sodiums do I need? 2 sodiums and 1 oxygen. Because each sodium loses an electron, each oxygen gains an electron, and remember we need to be electrically neutral, right? And so what we're going to learn on Monday is that chemical compounds are simply recognizing that we gain and lose electrons, and we have to make sure that we remain neutral overall, meaning we can't create or destroy any matter until chapter 23. And then what charges that go here, we just look up on the table, because I'm not going to look at them. Now, in chapter 7, you'll learn why they do it, but in chapter 2, we can just say, look it up on the table. So one of the things chemistry always does is says, here's the minimum amount of information you need to learn some stuff, right? We learn. Then we go, we want to learn more or have a deeper understanding, add a little bit more to our understanding, and then we can learn a whole bunch more stuff. Okay, that's it for me. We have a test on Friday, right? You guys can come in at 7:45 and sit here and take the test along with my other chemistry class. There should be enough room for everyone. You're not required to come early. I'm just saying if you want to, like, you know, if you're going home and you want to hit the road earlier, come here and take the test. If you don't want to take the test early, come in at 9:15, right? Yeah, exactly. And you guys are going to go rodeo, right? So you're going to take the test Monday at I'm lecturing, and so you're going to be listening to my lecture. Well, Monday at, say, 10:30, let's say? Or do you have how about after lunch, let's say, like 12:30? Well, I have scuba at 2:30. Yeah. I will be up, but I'll be about 6 a.m. and just getting out of the shower and eating breakfast. Yeah, not going to worry. How about you do it at 10:30 and you do it at 12:30 or 12:35? And then no one else is missing Friday? Okay. So that's a good one then. If you guys want to stick around and ask questions for 15 minutes, you can. And realistically, I have office hours, and I'll be in my office until 1:30. So I guess I will just shut this down. We'll adjourn. If you have questions, you can ask them over there. Oh, I guess let me do this real quick too, because I haven't updated ChemHaven. Remember, Thursday is Lab 2 in Allsbrook. Yeah. 106. If you want to bring a laptop and use your laptop instead of the computers over there, feel free. What? Means flip-flops are okay, dude. Friday, test over Chapter 1 and Lab 1, essentially. And that means next week, Monday, we're going to do elements 60 and then homework 2A and B are due. That's why I said I haven't updated Chem Haven. I'm slacking off this week. I'm coming to class late. I'm leaving notes behind. I'm a mess. Hopefully you guys are not as messed up as I am. Go do the practice test. Come ask me questions, et cetera, et cetera. Well, it's not really a practice test. It's just old test questions from the last, like, 10 years. Turn in giant piles of homework because really, oh, I forgot. I had some homework to hand back to you. Where's my pile? My bad. Sorry. I got homework to hand back. Going on away. Hey, did your test now? I think it's pretty cool. No. I had to pick it. Yeah, well, I have a class at 6. I won't make it out in time. On my note, no, he left. He left. He got accepted to dental school. Well, he's like, he's looking. Parker. That is all I have for you. So, have a good day. I'm chilling out in my office till about 1:30ish, and then I'll be one up to you. Meaning I can download the file, I can convert it, and I can upload it to the physical file. And then do that. Yeah, I'll show you. Let me show you quick if you want.
When did you
oh, wow, did I forget to hit off? When did you want to do what? Like try your gear out and stuff? I don't know. I guess you could come down to the pool